All right, welcome. The purpose of this video is to walk through the Sn2 mechanism. Sn2 stands for nucleophilic substitution. Substitution. 2 means that both reactants determine rate. Both reactants determine the reaction rate. All right, so I have an example here, iodoethane and sodium hydroxide. Let's take a look at that. Iodoethane, ethane, 2 carbons with an iodine atom attached. I do indeed here have a halogen alkane. And NaOH, aqueous, so that means in solution. It breaks up into its ions, sodium and hydroxide. I have a substitution reaction. What does that mean? Well, it means that my OH is going to substitute with my iodine. What will that look like in my final product? I'll have the same carbon chain that doesn't go anywhere. And I get a substitution. Instead of an iodine, I have an alcohol there, and then everything that's left over will get together. So my sodium ion and my iodine, and I'll form sodium iodide. All right, so how do I know I have an Sn2 mechanism here? Well, OH minus, this is indeed a nucleophile. It has a lone pair. It is electron rich, so nucleophile. I see I'm doing a substitution reaction. Why is it Sn2 and not a different nucleophilic substitution, which would be Sn1? Well, because Sn2 is the primary, or the preferred mechanism, I should say, for primary halogen alkanes. I do have a primary halogen alkane here because the carbon that my halogen is attached to just one more carbon. So Sn2 is preferred for primary halogen alkanes, less preferred for secondary, super less preferred for tertiary halogen alkanes. So primary halogen alkane, I have a nucleophile doing a substitution. That's leading me towards Sn2. All right, so how does this reaction actually take place? I see the reactants, I see what ends up, but how do we go from these reactants to these products? Well, that's why we need to take a look at the mechanism. So let's get into it. We need to be really, really specific when we draw the mechanism with the shape that the molecule forms. So I'm going to look at this mechanism starting by focusing on this carbon here. This carbon is the important carbon because it's the carbon that's going to be attacked in the mechanism. And yes, the word is actually attacked. So this carbon is attached to an iodine atom. And now I need to draw everything else that it's attached to, and I want to draw it in such a way that I'm leaving space for the carbon to be attacked, because the carbon does, the entire molecule does need to arrange itself so that the carbon can receive what's called this backside attack by the nucleophile. I know that sounds a little silly. Backside attack. It sounds like a I don't know, video game perhaps, but that is indeed what it's called, a backside attack. All right, so I'm going to draw everything that's around the carbon in a way that would allow the carbon to receive that backside attack. So I have my bromine here, or excuse me, my iodine. I am going to draw my hydrogen, and that is, let me indicate for you. Let me show this with a different color. The hydrogen I just drew is the one I put in yellow. I am now going to put the CH3 group down here. And if I wanted to show correct stereochemistry, I absolutely could. the hydrogen, getting a dashed line, the CH3, going behind. For the IB, you do need to show the order correctly. You don't actually need to show the wedges and dashes, just so you know. And then, so the CH3 that I added is this CH3. So what have I not shown yet? This hydrogen. I'm going to show the hydrogen going straight up. Now, cognity shows a hydrogen here and the CH3 going up. That is also correct. Of course, these are single bonds. These can rotate. I'm showing it in this orientation because that's how it's shown in the IB mark scheme, but either is correct. The way cognity shows it as well with the CH3 on top and the other hydrogen going back also works, also great. All right, so let's take a look at my ethane molecule that I've drawn in this really particular way and figure out why is this carbon so susceptible to a backside attack? Well, this CI bond I have, what kind of bond is this? I'll pause for a moment. Hopefully you're thinking to yourself, that looks like a polar covalent bond to me. And if you were thinking that, you would be right. This is a polar covalent bond with the carbon being partially positive, the iodine being partially negative. All right. And so if I have a partially negative thing and then my OH for my reactant comes along, and I'm going to draw this OH really specifically, I am going to include the lone pairs. I'm also going to include the negative sign, very important. I drew it as HO so that the O atom was really close to the carbon atom because it's the oxygen that's going to actually attach to the carbon. Okay, so this comes along. I have this negative species, this nucleophile, this electron rich. Well, take a look here. I have a negative thing and I have a positive thing. That's the basis of chemistry. Negatives and positives want to get together. So what's going to happen? My nucleophile is going to do a backside attack to my carbon. It's going to attack the carbon. So I'm drawing the nucleophile attacking the carbon. Remember that in a mechanism, arrows indicate the movement of electrons. If I draw a full arrow, that's 2 electrons. If I draw a half arrow, that's 1 electron. So in this case, both of those electrons from that lone pair are going to attack the carbon. Now the carbon's going to have too many electrons. It's going to need to get rid of some. So both of the electrons in this carbon iodine bond are going to get transferred to just the iodine so that it can leave, so that that atom, or it would actually be an ion in that case, so that the ion could leave. Notice this is heterolytic bond fission. Both of the electrons in that bond are getting attached to this iodine would then be called a leaving group, getting attached to the iodine. I have a full-headed arrow, so that makes it heterolytic bond fission. Unlike when we formed free radicals back in free radical substitution, and we did homolytic bond fission, and only 1 electron went to the leaving group. In this case, both of the electrons in this bond are getting transferred to the iodine. Now, before we end up with our beautiful alcohol product here, we get this transition state. The transition state is not very stable, but it does exist, so we do need to show it. How am I going to show the transition state? Well, I'm just going to follow along in the molecule. I have, one moment, let me find yet another new color to show you. I have this HO. All right, so HO. When that attack happens, the HO is now connected to the carbon, but it hasn't fully formed a bond yet. So we show this unstable transition state using dashed lines. So we have the HO doing the attack while the iodine is leaving. So in that transition state, in that unstable transition state, the HO is attacking, the iodine hasn't quite left yet. So we show these two species connected to the carbon with double bonds. All right, I'm going to show, of course, the carbon still has the hydrogen It still has that CH3, so I'm getting those from here and here. They just get repeated. And then I have a hydrogen, and let me keep my colors consistent. There's already plenty of colors in here. A hydrogen that goes on top. Very importantly, we do need to show that the negative sign is still there. That negative sign from the alcohol didn't go anywhere. Your transition state is indeed negative. All right, almost there. Let's go ahead, form our product. So notice where the things attached to the carbon go. We have carbon and hydrogen that are attached to the carbon that we're interested in. In the transition state, they're just kind of staying attached. And this is where that inversion happens, like we saw in class. It's sort of like an umbrella flipping upside down. So let's take a look at what that looks like. So these groups get inverted. All of a sudden, that hydrogen that was coming forward is now going back. This hydrogen, this methyl group, excuse me, is now coming forward. And my OH group, I am going to show right here. So the important thing, if you don't draw it with the wedges and dashes, that is also okay. But it is important to show, make sure you're connecting the carbon to the oxygen atom, not to the hydrogen. It is important to show that these substituents kind of move over to make room for the alcohol. That's how we show the inversion that happens in my reaction here. So you can show it like this. You can also show it with the wedges and the dashes. Of course, the hydrogen didn't go anywhere. And so we now have ethanol. The ethanol would continue to rearrange, needless to say, but this is how we need to show it in the mechanism, either with wedges and dashes, like I show here, or you can show it with straight lines, making sure that you're being careful to move these two substituents that you had over and add the alcohol on the left side here. That shows that it did the backside attack and that the molecule inverted. It flipped around. The CH3 and H kind of flipped around there. Okay. The other thing I would add, of course, is you end up with I minus because your I left, so you have your iodine ion. All right, I hope that helps. Let me know what questions you have. Practice will make better in this case. Working through the practice problems that we had from April 8th, I think will really help getting this mechanism down.